Yes. I will refer all questions to Srinivas. Yes, big Srinivas. Okay. Okay. Oh yeah, I am. Yes.
Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RVCCPS IAAC. It is my pleasure to introduce today's speaker, Dr. Dheeraj Narasimha. He will be speaking on a mean field game approach to resource allocation in communication systems. Dheeraj Narasimha obtained his PhD degree from Arizona State University under Professor Laying in 2021, while working on mean field games for density-dependent continuous time Markov process. He then went on to do a postdoctoral fellowship under Professor Srinivas Shakotai at Texas A&M University, and then completed a second postdoc at INRIA CNRS under Dr. Nicola Das. His work on mean field games has won runner-up best paper prizes in ACM Mobico, as well as most recently in IEEE Infocom. The main focus of his work revolves around solving decision problems with many participants under weak interaction, be it through weak graph limits, potential games, or mean field structures. Over to you, Dheeraj.
Thank you so much. It's a very nice introduction. I'm very grateful that I've been allowed to talk here. So I'm going to mainly introduce the idea of using mean field games to allocate resources in communication networks. So without further ado, let's begin. So this work mainly spans two papers. The first is the first paper I'm going to introduce is my most recent work with Parimal, who's sitting in the audience. Srinivas, who we're going to, if he comes, we're going to refer all the questions to. Srinivas from Texas A&M and my PhD advisor, Lay. So the first three were the ones that were responsible for the first paper I'm going to present. And then me, Srinivas and Lay worked on the second paper. If we have time, we'll touch upon the second paper. If not, we can talk offline about it. But let's move on. So the first paper I'm going to present is work where we're going to use mean field games for load balancing. The title of the paper itself is The Power of Two in Large Service Marketplaces. So in the system, we have a set of arrivals to a dispatcher and a collection of n servers. So these servers can either be idle, which I indicate in blue, or they can be busy, right? and tasks arrive into this dispatcher, and then we need to assign them to these servers, right? Now, since there are n servers, we have to ensure that we have n lambda arrivals. Otherwise, the problem is no longer interesting. And we assume that each of these tasks has a valuation function, which we know, which is called G. So each task comes in and it has a random valuation, which is distributed according to the distribution function G. Now each server picks a price, and what the dispatcher does is it picks a random collection of servers. It finds the minimum price of all these servers, and then if the valuation is higher than the price, the task goes into the server and the server becomes busy, right? So this is the basic mechanism that we have, right? So now we can divide these our mechanisms based on a few different things. The first thing we're going to do is look at routing. So if I deterministically pick an idle server at each time, note that all of these servers are homogeneous, so it doesn't matter which server I pick. That's a deterministic process where you pick an idle server at each time, and I call that model D1C. Right? If I decide to pick one arbitrarily at random, then this one we call R1C. Now notice that in the first case, I needed to know what the state of every server was. And in the second case, I don't need any state information. Finally, in the third case, what I do is I pick two servers at random. I can pick some finite number, but I'm going to pick two because that makes analysis a lot easier. And in this case, I don't need any information at all to pick these servers. So I might end up accidentally picking two busy servers, or one idle, one busy, or both idle. And now, once again, each of these servers is going to pick a price. If the server is busy, of course, the price is set to infinity. And if the valuation is higher than the price, once again, we join. Now, the second portion is how exactly do you decide the price? So in one case, what I'm going to have is a centralized pricing mechanism where everyone chooses essentially the same price parameter. In the second case, what I'm going to do is say there's no coordination at all. So the centralized pricing mechanism I'm going to call R2C, and the mechanism where everyone chooses a different price based on some parameter is going to be called R2G. So this is the version that we're going to mainly analyze. So here there's actually a game because I'm going to pick two people at random and they're going to compete against each other if they're both idle. Right? I want to pick the lower price because the lower price is the guy who's going to win out and get service. And every time he gets picked, he gets a revenue proportion exactly equal to how much price he paid. Right? The task simply leaves. Yes. So the initial thought I had was when I used to come here when I was really young and I used to get off at Bangalore station, two auto drivers would come and yell at me their price for going to Vijayanagar. And if both of them were too high, I would just skip and go to the Majestic bus stop and take a bus and say, I'm not waiting for you guys to arrive at a lower price. So one of the cases where this is where this occurs is when as time has progressed, the amount of edge servers and sort of these ad hoc communication resources have grown. But sitting and finding good coordinated ways of allocating them it requires a scaling of infrastructure. And here what we're trying to do is say, okay, no, we may not need all that infrastructure to find good routing protocols because that requires a lot of information. Here's a method which requires no coordination and no information. And we're wondering how good is this at the end of the day? And what we're going to say is, well, at the end of the talk, what we're going to sort of conclude is the information bottleneck is significant, but the coordination aspect of this is not going to be the big problem in this case. But that is the basic idea for this. Another example might be some cases like platforms like Namayatre, where you're sitting and trying to get auto drivers to coordinate. But I think there's it's a little more one-sided in terms of the platform, but I think in Uber people can reject and accept based on whether or not they think the value is better. So that is another example. So we're going to build it into the model, but we're going to make them stochastic. And in fact, for analytical tractability, because we have a minimum of pricing distributions, they're going to be exponential. We'll bring that up later. Yes, yes. So who is busy, who is not, is going to be the full information problem. Yeah. But the much simpler version is what's the fraction of people who are busy. That is a much simpler thing to keep track of. And in fact, it will slowly get to the point where you can sort of determine that if you know the price or the pricing scheme. So the rate at which you start off by assigning them, but then there's a random amount of time it takes for the server to complete the task. So so the server needs to, each of these servers will have to send a message back to the dispatcher saying, hey, I'm free now. And that is a huge communication overhead, or at least a communication overhead. And so where that makes the task a lot harder than simply keeping track of who I've sent it to, because I also have to know when they're done with the task. And here we're assuming that all the rates are 1. Better. Great questions all. Okay. Oh, and I know I didn't say this in the beginning, but please feel free to interrupt me whenever. Yeah. Okay. So, all right. So now what we have is a system where we have a single tag server. And what we're going to look at is this view where I'm going to look at just the first tag server and the rest of the system. And the first tag server has essentially 2 states, he's either idle or busy, right? And the rate at which he goes from idle to busy will depend not on the exact states of all the people in the system, but only on the fraction of people who are busy, right? Because each person is being picked uniformly at random in the R2G model. And so what you can actually, you need a very little work, but it's something worth doing, is to notice that if I were to take the system as a tagged agent and the fraction of busy servers, then this joint system is essentially Markovian, right? This is a note about the generator. I know there are people in this audience who really note these sort of things, which is why I think it's worth clarifying. Right. And each server wishes to maximize its average, the average price that it can charge, where CK is the event that a given task gets accepted into the tag server, right? So this is the server bids the lower of the 2 prices, it's idle, and then a task came in, it got busy because its valuation was higher than the price charged by the server, and so the server got a price PK, and then you sum this over time, and as limit k tends to infinity, t tends to infinity, what we're trying to do is maximize the average price charged by the server, or the average reward of the server, right? So now notice that each of these servers are doing exactly this. So what we have is a fairly complicated game, right? Because each person might choose a different price value, and because each of them chooses a different price value, that determines a different Markov process on underlying Markov chain, and and that's going to affect the total fraction of busy people in this system. So one way that the tag server views this problem is it's choosing some price P0 based on some distribution. This will determine its belief about what the fraction of busy people are. This in turn will determine how much revenue it can gather. And based on how much revenue it can gather, it's going to try and do a best response strategy, right? And in return, and this best response strategy will sort of give it a new price distribution. And then this whole thing happens again. And this is a fairly hard problem as the number of people grow large, because I have to worry about what every other person is doing in the system. And now we enter the eponymous mean field games. So what we have is what we're going to do is we're going to say, okay, I'm the tag server. I'm going to assume that all the price parameters that everyone else has chosen is fixed. And given that everyone else is fixed, what I'm going to do is, try to find the best response. And now in order to do that, what the main result we're going to leverage is that the system's so created where I get to choose my price, but everyone else is fixed, has a very nice property, which is the mean field property, right? What this value is going to converge to is a fixed value as n tends to infinity, which is time invariant. What I mean by time invariant is that the fraction of busy people converges to a constant, right? So to state this explicitly, the stationary fraction of busy servers converges in the mean square sense to a fixed value z star. And this value is order 1 over n in the mean square sense, right? So not only do you get a rate of convergence result, but you also know that it's a point mass as t and n tend to infinity. And here z star is the fixed point of the McKean-Blasov equations. And you can derive this fairly simply if you using detailed balance equations for this problem. I have a final slide which gives exactly how you go about doing it. But for now, let's assume that if you know, you can do this simply by looking at the detailed balance equations of the tag server. Right. So now what you have is that the tag server is trying to find its best response. But we know, and here I would have liked to thank Srinivas if Srinivas was around, that as the number of servers tend to infinity, the actual fraction of busy channels actually converges to a constant that doesn't depend on time, right? And now, so in order to prove that this actually happens, you need these 4 conditions. So the first condition is bounded transition rates. The second is bounded number of transitions per second. The third is that the generator converges to the McKean-Blasov equations, and that the mean field limit, the McKean-Blasov equations, which are an ODE, are exponentially stable. So now one thing to note is that our state isn't the most conventional notion of state that people use. Usually people would simply keep track of the fraction of busy channel. But in this case, we have an additional fraction, an additional portion, which is the tag server state itself. So writing the generator is a little trickier than normal, but it works itself out. And Parimal did a great job in this portion. And he deserves a round of applause for it. Okay. And now the McKean-Blasov equations that you derived from this is exactly the generator function times the transition for the fraction of busy channel. And then you look at it and the limit as n tends to infinity. And what you get is something of the form, an ODE of the form z of t is equal to h of z, and you can show that this is exponentially stable. And one of the reasons why we have a fairly nice result like this is you can explicitly work out the exact dynamical system in this problem, right? In most problems of this kind, you typically need Lyapunov stability, but we kind of managed to avoid that by using closed form expressions and bounds on this. So most of our results in this paper were a more direct approach towards proving the mean field result, as opposed to how a lot of other results, which are verification theorems, turned out. Yes, but it's a autonomous system, but yes, H of 0, yes, yes. 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 Yes, yes, that is so one of the main reasons it works out boils down to this. No, it's specifically that my transition rates explicitly only depend on the fraction of people you pick, because what I'm doing is I'm choosing, if I can choose some finite fraction of people at a time, or I think you can actually go a little further than that, but that's a little trickier. And what happens is, I don't think so. It works out. So therefore, it's only dependent on this density, and that's what works. That is the main reason it works itself out. In fact, you have other results that indicate things like ICT, internally chain transient case, in these sort of cases as well. So the original results of Kurtz explicitly use these sort of ideas of the generator on specifically these empirical measures, right? Yes, yes. Uh, I don't think, or rather, I'm not confident it will work. There are recent results on queuing systems by Lei and Shin, which suggest that it might work even in heterogeneous systems, but I'm not certain it will work for any model. So the mean field that I'm wielding like a hammer here, I don't think it will directly work. There may be some way to make it work under O of 1, but that's not something I can guarantee. Actually, up to log n, it still works. But that is again for a queuing result, but that one I know how it was done, so I think I can move that there. But beyond log n, I'm not certain it works. Right. So now, if I'm the tagged server, my belief is, given the parameters of my own system, I believe that the rest of the system is basically at a fixed fraction. And now, or rather, the rest of the system occupies a fixed fraction of, or the rest of the system has a fixed fraction of busy servers. And that sort of tells me something about, about how I can optimize this price, right? Now, it turns out that if I choose an arbitrary price, because I'm doing the minimum of 2 distributions, things can get a little sketchy. So for now, I'm going to make a simplifying assumption. We did go beyond that, at least by using this model as a heuristic to do more general noise models. But for now, I'm going to assume that all my prices are exponentially distributed. My valuation is exponentially distributed. And the main reason for this is because the minimum of two exponential distributions is still exponential. So the analysis works itself out. This is mainly for analytical tractability. Right. Okay, and I assume that my own parameter is D0, which I can control, and everyone else chooses the parameter D1. Right. So the mean field result itself only needs you to have a fixed distribution. The next few results will require this sort of heavy assumption on the pricing, mainly because all of our expressions are closed form, or we wanted closed form expressions. So given that everyone chooses D1, the fraction of busy channels is Z star. Given the fraction is Z star, I can now explicitly compute what my reward, long-term average reward is, and then I'm hoping that it's an expression that I can use to find a good best response. And that is precisely what theorem 3 is about, which is that you can explicitly compute the fraction of the average reward that you obtain as time tends to infinity, and n tends to infinity, which depends on your own price, the assumed price that everyone else picks, and the fraction of busy channel. And what that gives you is a way to compute the best response. And it's the parameter, yes, for a randomness, yes. Right. And what it turns out that given that when D1 is fixed, the response is unimodal. And this is actually fairly hard to prove, but yeah, because it's not strictly speaking concave. And given this, you can actually pick the best price, and it's unique. And because it's the argmax is unique, the best response is continuous. Right? That's important to note for when you want to show a fixed point theorem. And so now what the mechanism looks like is you start off with some D1 and D0. You compute Z star. You can compute your average reward over time. You get a best response D0 star by computing the maximum of a unimodal function. And now this is the view that each tag server takes. There's nothing special about the tag server you picked, which means everyone is going to adopt this value. And so what you get is a closed loop system where you start with some D1 and then you end up with some D0 star, and you keep doing this. So now, because of continuity, you know that at least one fixed point exists for this loop process, standard Brouwer's point theorem, Brouwer's fixed point theorem. And so you know that at least one mean field equilibrium exists. All right. But how do I compute this? Turns out for this problem, it's not that hard to do. So first what I do is I pick a D1. I compute Z star of D1, compute the best response. And this gives me a D0, a best response D0. Pick a collection of values of D1 and interpolate them. What you get is some curve. And that curve needs to intersect with D0 equals D1 for it to be a fixed point. And each of those fixed, yeah. Yes, yes, yes. So D0 is a parameter I can control, but yes. Yeah. Z star doesn't depend on. Yes, and then you pick the best D0 star at that. Yes, yes. Largely because in the density dependent first. Right. And so each of these is for a different arrival rate. You can explicitly compute the curve, the point where the two curves meet, and each of these curves of intersection now become the now become your mean field equilibrium. Yeah. Is the D? Yes. Yes. So essentially what you're doing is you're computing the best response and you're interpolating to find each of these curves. I'm sure there are more efficient ways to do this, but what you're currently doing is picking, what we did was just linear interpolation, using a bunch of, using a fixed bunch of points and then computing where the two of them meet. Yes, that is part of the unimodality proof. So there is unique, yeah. Yes, you can prove that it's between 0 and 2b. B is the parameter of the valuation function. And in fact, if you normalize it so that they're all 1, then they all end up being exactly the same. So you can actually ensure that they're bounded. And we usually normalize the whole thing to 1 because everything works out to be that. And so here are so we can't, because we don't have exact closed form expression, it's very hard to prove that this is a contraction mapping. And because it's not a contraction mapping, it's not, cycles can form and you can jump between two values if you just keep doing that naive. And yeah. Oh, so one method which I think I discussed with Rajesh yesterday is you might be able to slightly modify the reward function so that you add a KL divergence term, a tau times KL divergence term, and slowly bring that tau to 0. And if you pick that carefully, your best response will be your price parameter will be along some distribution, will be exponential over something. But what you can then do is sort of slowly bring that tau to 0. And so for a very high value of tau, what your price parameter will be might be just some uniform value. But as tau tends to 0, this schedule will probably. But don't quote me on that for this thing because this doesn't have, you'll have to do an action discretization to make it work. So you'll have to be careful there. And it's non-trivial, but yes, you're right. There will be, you can probably do some sort of damping, or you can do small updates on your price parameter at each point and slowly force it to go towards its fixed point. But possibly. Yeah. If you make the KL divergence term really large, like the tau times KL divergence term really large, it's very easy to show that the best response will probably be a uniform distribution over those price parameters, right? Because essentially the best thing you can do at that, more like an entropy term with normalized by some uniform distribution. And then once you start there, what you do is you slowly bring that tau down. And because then you will probably move, you'll be close enough in the vicinity of the fixed point each time you change tau, that it will, I'm not saying it will definitely work, but that might be a heuristic that could work in this case. I think it will be close to, it might be a sort of 2 times scale update in those sort of problem in that sort of case. And I don't know And it remains to show that at least in the local neighborhood of each of those fixed points, they are attractors. But if you do that, then I have a feeling it will work itself out. But I don't necessarily know. And this approach of numerical computation works. So that's kind of where I'm going with this. Yeah. But you're right. And for more general games, there might be a real place to ask how do you come to the right parameter, and there's a lot of work on that too. Okay, so here are some results. Again, thanks to Srinivas. And so if you notice, the brown line is D1C, which is the case where I got to always pick an idle server. And it beats out all the other protocols by a big margin. All the other mechanisms by a big margin, because essentially you're always scheduling to someone who's idle. Now, the next two, which we found kind of surprising, is when you choose two at random and you play the game in one case and you choose a centralized pricing that maximizes your revenue in the other case, they're almost identical. They're not exactly identical, even though they appear exactly identical. They're almost identical. And what this indicates is that the main barrier to earning a huge revenue is the routing part. The coordination itself, you can actually, if you look at the plot of the price of anarchy, actually goes to zero very quickly in this case. Of course, we don't have closed form expressions for the price of anarchy, but you can explicitly check this, or rather you can explicitly see this in this case. And finally, the R1C is where you randomly pick a server, which requires no coordination, no information, but it's always going to perform really poorly. So you get a major jump from choosing just one server to choosing two. But from two onwards, if you want a lot of improvement, you probably need to start picking an order n kind of problem, an order n or so to get to the kind of revenue you see here. Also, in our paper, we have analytical expressions for all the other routing mechanisms and pricing mechanisms, specifically for this system. Right? So you can check those as well. All right. So I think I have time. I'm going to drone on for another 5 minutes or so. After that, I'll take questions. So the second place where I'm going to talk about resource allocation is in the carrier sensing case. So what I have, so these are wireless sensor modes that I used to work on as an undergrad. And all of these modes are basically going to be deployed for temperature sensing. So I have one central node that all these nodes are trying to send messages to. And there are two channels available. And right now, the first channel is being occupied by node 1 and the second by node 3. And they're using this channel to send their readings to the main node. Meanwhile, channel node 2 has a reading and he tries to probe the second channel and he finds that it's busy. So this is classic CSMA. And now, because he's unsuccessful, he can't transmit. And what happens in the interim is while he's exponentially backing off he gets a new reading. The new reading is going to replace the old reading. So this is our basic system model. And what you can see for this device model is a fairly simple system. I start idle, I take a reading, so I wake up at exponential times, I take a reading, then I start looking for channels. My probability of success depends on the fraction of busy people. If I find a channel, I'm going to start transmitting, and then and then at rate 1, it gets through. If in the interim a new message comes in, I'm going to hold on to the channel and try to but again, which is why it's 1 over 1 plus lambda. And my utility function in this case is going to be based on how much the cost. So this is minus, since I'm trying to minimize the cost, is how much time do I spend in the probing while I'm transmitting, and the probe, and then of course I'm going to pay money for probing. So that's the rate at which I'm probing times how much time I spend doing it. Right? And you can once again formulate this as a mean field gain problem. And using the exact method, you can actually show once again that you have these updates. And the question you have is, what's the best rate of probing in this problem? And what we showed is that you get in this case, what you can show is you have a mean field gain equilibrium in some cases, and you don't have mean field gain equilibria in a certain region. And in some cases, you should just choose to transmit at the highest rate possible. You should try to probe at the highest rate you have available. And so those are the three cases for this problem. So this depends heavily on the parameter C you choose here, which makes sense. If C is really large, I might choose never to probe at all. If it's really small, I might choose to probe constantly. So again, this is case 1, where T star equals infinity, which is quote unquote, which means just try to constantly look for channels, or try to look for channels as quickly as you can. Case 2 is a nice case where I can explicitly compute what the mean field gain equilibrium looks like. And there's a little middle case here where essentially you jump between two. No Nash equilibrium exists, actually. No fixed point exists. And one of the reasons that happens is because your arg min in this case turns out to be discontinuous. All right. So this is actually a combination of the arrival rates as well as the price parameter. So for a fixed price parameter, you tend to see this sort of. All right. Yeah. D is the probing rate. So it's the rate at which I look for channels. Lambda is the arrival rate. Sorry. The number of nodes is. The number of channels are proportional to the number of nodes. Right. And in this case, the question that Aditya asked actually works itself out. You can find an explicit parameter in Cm lambda, a value of the parameter, where if C is greater than that value, you actually get a contraction mapping. And so what you can do is repeatedly do the naive thing and get to the best value, the best response. And in this case, we can also characterize a closed form expression for the price of anarchy and show it's bounded above by 1/2, which means at worst you lose as compared to the fixed, as compared to a case where you try to maximize the or minimize the cost jointly amongst all of them. You can actually just choose, you can choose to do it in a distributed fashion, and at worst you lose about half the utility in this case. So to summarize, we have a game with many players, and we want to find a distributed solution to this problem. But we want to minimize the amount of information, and we want to minimize the amount of coordination. So but hopefully if you have density dependent interactions, then you can treat this problem as a mean field game, and hopefully your solution is simple enough that you can compute Nash equilibria in those cases. Right? And that becomes a distributed way of solving, at least to get Nash equilibria in many of these problems. Right? So thank you. And okay, right. Thank you. In case anyone wants, here's a scary slide for the generator function. I stole this from Parimal. So essentially, the explicit value of the generator for this joint system can be explicitly computed, and it looks like this. So the top two indicate how the fraction changes, while the bottom two indicate how the tag servers rates, how the tag server rates change, or the rates of the tag server. And basically what we're interested in is the top two in the limit as n tends to infinity, which is why we get the McCain-Blasov equations that look the way they do. And you can explicitly compute Z star in these cases. And so this was a scary slide. Yeah, thank you.
Thank you, Dheeraj, for an interesting talk. Are there more questions from the audience?
Yes, I think a lot of different communication problems or load balancing problems can be modeled so long as they are Markov processes with a lot of players. I think you can mean fields have a place, especially considering the recent works by Shin and Lei on heterogeneous systems. The main difficulty I anticipate with mean field games or mean field models is that the dynamical system aspects of these problems tend to are quite challenging. Basically, you need to show somehow that this joint dynamical system has local exponential stability, global asymptotic stability. Those sort of things are highly non-trivial for arbitrary systems, and they become much harder when you want to do heterogeneous systems. The other aspect is you want to be able to expand the Stein's method to more heterogeneous systems, right? That is actually the method that was used to prove the original mean field result, or at least what we call the modified version of Stein's method that we use in our proofs. And each of those things are heavily application dependent, right? It's not a one size fits all, but I do anticipate that I will be using mean field in a lot of these problems, but it will be heavily application dependent. One example where I didn't explicitly use the methods here, but I did use the kind of concentration result was in the proof of heterogeneous restless multi-arm bandits. There you might use more standard concentration results, but the basic idea remains this idea of weak interactions and trying to come up with good concentration bonds in those cases. Also, the approach that even though the exact approach of using mean fields to solve this problem may not always be applicable, the Stein's method and the Stein operator can be exported to stochastic approximation settings. And there's a very recent paper by Shrikant that talked about using Stein's method for stochastic approximations. Even Nicola has a paper on it as well. So Nicola has it for constant updates in constant step size updates in stochastic approximation, and he gets an exact quantification of how far your system will be in the limit as time tends to infinity from the fixed point. Similarly, Shrikant managed to show a CLT theorem for Markov noise problems in many other using essentially not this version of science method, but along these lines, a more developed version of these problems. So while the exact method might not be directly applicable, I think versions of this method are still highly relevant. So what happens is it jumps between two extremes, and what I plotted was the average. So it's not really the thing. So I picked it at 1,000. So that was where it was jumping between. So in this paper we couldn't say it, but in the paper, in at least the results where I had the tail divergence, you could explicitly talk about this problem doesn't occur because you've expanded the size quite a lot of the domain. So you actually get that it smoothens it out, and you can show that you have this randomized strategy over the set of possible values you can choose in the discretized set of values. Yes. If we don't have uniqueness. No, so this could have very well been a sort of weird curve where this intersected at more than one point. Yes. 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 That this itself has some sort of nice unimodal structure, and unimodality wouldn't have been enough. Yeah, is monotonicity enough? Like I can have some curve like this and some curve like that such that they intersect at maybe 0 and another point kind of, and you can reject one of them. Yeah. But you will probably have some nice. So at the end, once you get this, you probably will, if you have multiple points, you can choose which one. But that becomes more of a manual argument. It's like, I have decided to choose the better of the fixed points. So I don't necessarily say that this is where things can settle, but the devices would probably pick the one with the higher revenue rate, the equilibrium corresponding to the higher revenue rate. Because each of these equilibria will give a corresponding revenue rate. So you can view this as a one-shot game where I start off with this model, come up with all the fixed points, and then choose the one at that Nash equilibrium point. In which case, I would pick the one with the highest revenue. This is a Nash equilibrium, which means that if you deviate, you have no incentive to deviate once you are at that point. Yeah. Right. Right. I have no idea how that would work. Well, right. Right. Yes. Yes. Right. Yes. Yes. So the rate of convergence will be order cube 1 over cube root of n. So if I have any finite n and one person chooses to deviate, the maximum they can benefit from it is order cube 1 over cube root of n, which tends to 0 as n. I don't know if you can actually bring it down to 1 over n, but this is a fairly loose boundary. I'm sorry, I couldn't quite hear you.
If we are showing convergence to the limiting equilibria,
Okay.
then do we also need to argue that the limiting equilibria is unique?
Not necessarily. You can have multiple equilibria and you can say that you converge to one of them.
Okay.
I think the authority on that. But also Bruce had a paper, I think, from a while back on bifurcations and those sort of phenomena. And right. Also, I'm not even certain that these are the only equilibria, right? This is specifically in the mean field game approach, but there could be some completely different approach where people choose completely different action profiles, and those can produce Nash equilibria that don't get modeled by this approach. And all I can say is these are definitely Nash equilibria. But if I have a case where everyone has some different action, has a different action profile, I'm not certain that I can't guarantee that that won't be a Nash equilibria. Yeah.
Thank you everyone for attending. We have arranged refreshments for coffee, but please continue your conversations.
Thank you.